All right, so we're going to be in your notes for a little bit here. I want to talk about these trends. You should have a couple slides there or a couple notes. This is all the stuff that we've been working on. We talked about Dmitry Mendeleev and how he created his first periodic table. So this is the 6-4 section in your notes. So he organized those. He organized them in terms of atomic mass. He placed them similar chemical reactivities, and he had atomic numbers, which gives you your columns. So you guys have been working on that with your cards recently, forming those. These ideas that we came up with, you did that with your group and talked about how those are similar things. They have the same number of valence electrons. Okay. So then when you did your cards, we've still got some games to play, but we're going to talk about some of these trends before you get into any more of the games, okay, for Monday. So atomic radius, we talked about this one yesterday. We said as we move down the periodic table, the atomic radius is going to get bigger because we're adding more of those valence shells. So I've compared that to like those Russian nesting dolls, right? You start out with the one, and then you have the next one and the next one, and it keeps getting bigger and bigger. Okay, you've seen the Russian nesting dolls that I'm talking about. Okay, going from left to right, though, this is not quite as intuitive. Okay, going from left to right, you're adding more protons. So adding, you think it's getting bigger, right? So this is the one where you can't let your brain override, like your initial instinct override you. Okay. It's actually going to get smaller because you're getting a higher effective nuclear charge. You're adding more things that are pulling in on that atom. So as you move across in the same period, it's going to get smaller. Does that make sense? Okay. So that was our trend for that, and that has to do with effective nuclear charge. This is kind of a diagram of how these would look. As you're going down, it's going to get bigger. As you're going across in the same period, it's going to get smaller. And then they gave you a graph of what that looks like. Okay. Ionic radius. This is a little less, like, we got to talk about this. Okay. So we're going to calculate the Zeph of the following. Okay. So remember, what we do here is we take our atomic number. So for magnesium, our atomic number is 12. And we're going to subtract out the core electrons. But this is a +2 charge.
Where are you?
Right there. Okay, well, you got a little space off to the side to add it in, don't you? So I've got 12 protons here. I've got 11 protons here. I've got 10 here. I've got 9 here. I've got 8. Missed that guy. For my oxygen, how many core electrons am I going to have? I have 6 valence. How many core will I have?
How do you know 6 valence?
Because it's in the 6th column. 1, 2, 3, 4, 5. Or wait a minute, I'm missing something. 1, 2, 3. Oh, yeah, we missed.
Yeah.
4, 5. This is 6, 7, 8 on your periodic table. Okay. So if I have 6 valence, how many core do I have?
2.
2. So oxygen's effective nuclear charge is
Where's 6?
6. Okay. Fluorine, what is it? How many core electrons does it have? 2. Neon, 2. Sodium plus 1. So sodium sodium plus 1. What happens with the plus 1? How did I get the plus 1?
1 more ring around it.
It's a plus 1 charge. What charge do electrons have?
Yeah, you lose 1.
Right, we're going to lose an electron. Gone. How many core electrons do I have now? How many do I have on the outside right now?
8.
8. So how many core do I have?
Oh, you do have 2.
I do have 2. Magnesium plus 2. How did it become a plus 2?
2 protons added.
It lost 2 electrons. How many core electrons do I have?
2.
2.
So wait, hypothetically before, if it didn't have those 2 extra protons, what would the number of core electrons be?
If it didn't have 2 extra protons, then it's not going to be magnesium, it would be neon.
Oh. Then what would be the core number of electrons?
2. This is neon right here.
So it's always just 2 no matter what.
Well, for these right here, yeah. But if you got down to here, it wouldn't be. It would be
Yeah,
more.
yeah, of course.
So,
In the second row, I mean.
okay. So now we need to figure out ionic radius. Okay. So we are going to look at our effective nuclear charge, which we've calculated, and we're going to look at how many electrons these guys have. So oxygen has 6 protons, effective nuclear charge of 6, okay? Pulling on how many electrons? This has become oxygen because it's added 2 electrons. So how many electrons in the outer ring is that? Are these 6 protons, our effective nuclear charge pulling on?
8.
8 electrons. Because of that, it's not going to be able to pull as hard because it's got too many things to pull in. So this radius is going to be big compared to what oxygen would normally look like. Fluorine is going to look like this. How many electrons is it pulling on?
8.
8. So it's going to be bigger than what a normal fluorine would look like, but a little smaller than oxygen minus 2. So if that's my circle, now my circles become like that for the fluorine. Neon then, it has 8 and it's got 8, so it's going to be kind of our normal size here. I want to make that just a little bit smaller than this guy. Sodium now has 9 protons, effective nuclear charge of 9, pulling on how many electrons?
8.
8. So it's going to be even smaller. Magnesium then is going to have 10 proton, effective nuclear charge of 10, and it's pulling on 8. So it's going to be even smaller. So your magnesium 2+ is going to be the smallest out of all of these. Does that make sense? Why? This is a little harder to wrap your brain around. That's why you got to kind of internalize this. Yes.
How are you getting the -2?
Here,
Yeah.
because it's lost 2 electrons.
Yeah, but unlike the other ones, like neon, for example.
Like 10
It doesn't
minus
have any.
2.
Because those are the core electrons. So if this is sodium here, okay, sodium has lost an electron. So now this is the core, not this. These are your valence now, because it's lost that one.
Oh.
Also, any electrons that aren't valence electrons, they're core electrons.
Yes,
Okay. That's what I wanted to know.
Okay.
So how are you getting 8 for all of them?
because these have lost 2 electrons.
Okay.
So if this is magnesium and it's lost 2 electrons, I have 8 out here that are my valence. Okay, because I've subtracted my 2 away that are my core. So that's how I got these. And then I've got 8 valence electrons that that effective nuclear charge is raining on. Oh, cool.
The bottom of that is messed up, so we're reprinting it.
Cool.
Roll the dice.
Yeah.
D20.
The only problem is if it like rolls the same thing every time, then it's not going to work because, dice have to be weighted. So,
Borrow one of my normal D20s.
but these have ions on them, so that
Oh,
when
I
we
see.
start
Got
naming
you.
and writing formulas, I'm trying to do something kind of fun
Okay.
with you guys. So. Essentially, if you have more protons than electrons, it's going to pull it in tighter. If you've got more electrons than protons, it's going to be bigger. So if it's a negative charge, it's going to be bigger than it normally would be. And if it is a positive charge, it's going to be skinnier. It's going to pull it in tighter. So you've got more protons than electrons.
But like, for fluorine, aren't you just subtracting 1 because it has a minus? Like.
So I subtracted 1. This was figuring out effective nuclear charge. So don't let that confuse you. Okay, that's not figuring out number of electrons.
Okay.
This 8 is the fact that fluorine picked up an extra electron. That's why it's a negative charge. So it's got 8 electrons in its valence shell.
Okay.
Yeah.
That
Are you going to
also
have us
mean it
finish the
lost
homework
a,
next
pro-
week?
No, it can't lose a proton because then it wouldn't be fluorine anymore.
Oh, okay.
If it loses a proton, it's not fluorine, now it's oxygen.
Oh, yeah.
You can only lose and gain electrons.
Okay.
Protons can't be lost or gained unless you want to go through some sort of nuclear reaction,
Okay.
which we don't want to do. Am I done with time?
We have 3 minutes.
Oh, I still have 3 minutes. Okay. So, the other thing, oh shoot, I didn't mean to do that. So then we did ionization energy is the next topic. We need to talk about electronegativity. So electronegativity, I just want to talk about that real quick. Electronegativity is the measure of an atom to attract electrons. Okay, so when we talk about the trend here, we're talking about kind of how bad these things want electrons. And remember, everything is striving to be, and I'm personifying this, okay? These don't have emotions. Everything's trying to become a noble gas, okay? So when we look at our periodic table, all of the noble gases, for the most part, have a 0 electronegativity. They don't need an extra electron. They're already good. Okay, everything wants to be them. All right. Now, the stuff on this side of the periodic table, your non-metals, are wanting to gain electrons. Because if, like, fluorine gains 1 electron, now it's neon as far as electron configuration. It's not actually neon because it hasn't gained a proton, but it has the electron configuration of neon. And that's what they're trying to do, is get their electron configuration to look like a noble gas. Okay? So for these guys, they want to gain. So they're going to have a very high electronegativity, because if they gain 1 or they gain 2, now they look like a noble gas on the outside with the electron configuration. Okay? For these guys over here, our metals, it's easier for them to lose 1 or 2. If they lose 1 or 2, now they look like the previous noble gas. Okay? So they're going to have low electronegativities. So this is the trend for electronegativity. All right? And then we'll talk about ionization energy at the top of the hour on Monday. And you have your lab to do for homework. It is due on Tuesday.